this webinar series is sponsored by Qatar ITU Student Chapter and several UTC's University Transportation Centers, including NICER, CTED, and TomNet. So let's see. And today we are very happy to have Mr. Acey Roberts and Alex Koszegi. Did I pronounce it correctly?
Yep,
okay.
You did.
All right. Okay. Thank you. So basically, we have, you know, I know Acey actually for quite a long while. You know, when I was in Mississippi, he was with the Mississippi State DOT and really gave us lots of help and support during that time. Now, Acey is WGI's National TISMO lead, and he's got like 20 years of experience as a professional engineering, helping to advance traffic safety and technology improvements on our roadways. Particularly, he's helping design the largest autonomous straddle network in America in Jacksonville, Florida. We actually chatted about it before the seminar officially starts. It was really impressive. And we look forward to the lessons learned from that project. And he has a degree from University of Mississippi, Ole Miss, with advanced coursework in transportation at Northwestern University. Alex Koszegi, she's a technical sales engineer for DWave system. In this role, Alex helps identify quantum use cases in their organizations, teaches on virtual training course, and supports customers with their research and application development. And Alex had a Bachelor of Electrical Engineering at the University of Victoria. So today they're going to talk about a very interesting topic, quantum computing, and why do we need quantum computing in transportation, and how do we do that? So we actually have, this is like a hybrid seminar. So the presenters this time will do it online, and we also have a classroom of students here. So we'll have a presentation first for 45 minutes, and we're going to get to hybrid question and answers. And with that, I see the recording has started. Do you mind being recorded?
Sounds good to me.
Awesome. All right, I'll give the floor to you, and Acey, you may start. Thank you.
All right, thank you for having us, Dr. Lee, and we're very excited to share some of our thoughts about quantum computing and transportation. It might be a little bit early days to talk about some practical projects, but I really think that we are on the very cusp of seeing some real demonstration projects, and in fact we'll talk about some real demonstration projects that have happened across the country, and what they're trying to accomplish using next level computer systems in transportation. So I always like to, when I talk to students, to just encourage you and inspire you to think about the ultimate goal of what we're trying to accomplish as engineers, and that's to improve public safety, to make it make the world better for your community that you live in, as well as the general public. We do have a lot of problems in the traffic world, as you probably know if you've ever driven a car. The issues around traffic signalization and congestion and delay and distracted driving now, and just the impacts that human behavior has sometimes can be really dangerous, and 30,000, over 30,000 deaths every year on the roadways in America. That we really are taking it upon it as a mission to really reduce that. And in fact, USDOT and FDOT has made that a mission to approach zero fatalities on the roadways. So we've got to make some real changes and some real dare I say quantum leaps to make changes to our freeway and to the operations. So our work zones are really dangerous as we try to make changes to the roadways, and as we try to maintain our systems. That just creates another level of danger for the public. Transit, as you all know, has a hard time. It's really hard to keep the buses on track on the same schedule. There's a lot of factors that affect bus routes and transit, services in America. It's really hard to depend on transit services if you have a medical appointment or a business appointment. Sometimes delay and transit is not as efficient as we would like it to be, and certainly accidents. There's just so many fatalities and injuries that are unnecessary on our roadways. So, as we said, I'd like to talk about how we can use quantum computing to really start to address some of these issues. As I said, I work in traffic engineering for almost 20 years. Alex will talk about more of the specific quantum computing services and how that really works. Don't let me try to explain quantum computing to you, but I am very excited about the connected and autonomous vehicle industry and what that brings to our industry, and certainly ITS field devices as well. But the issue with those is that it brings sometimes terabytes of data to our agencies. Sometimes with vehicles, it's a terabyte of information every hour per car, and it's just really becoming too much information to really justify using it and to try to really handle it and manage it. I do believe that the more data that we can get, the better, but it's important that we're able to to use it in a usable way and without being overwhelmed. I think that's where we are right now. So quantum computing can be certainly one solution for that. As we talked about, 2020, was a terrifying year in a lot of ways, but certainly one way that was terrifying is that we saw the reversal of some really important trends. We had a lot of safety trends that were going down, as you can see, over the last few years before 2020, and then with the great reduction in traffic volume across the country, you saw a great uptick in the total number of deaths, which might be unusual or might not be what you expect, but it's really a direct correlation to the increased speed. As volume goes down, people were able to drive faster and potentially more dangerously. So, one issue that we talked about was how computing is just starting to hit its limit. Traditional computing systems just are having a hard time processing all of this information and all this data. One traditional computing problem that we've had in this industry is the traveling salesman problem, or the vehicle routing problem. As you can see here, it's just generally being able, trying to move through various cities, or I think a more modern approach to this problem would be like Amazon, where they're trying to make multiple deliveries, per day. And how do they do that efficiently? And so when you're making multiple stops and your variables at each intersection and at each stop, and signal systems and all these different variables start to add up at each stop, you can see how the variables tend to become exponential very quickly. You can see in the table at the bottom right, by a study done by Cambridge, at Mark Jackson in Cambridge, how quickly these variables just get out of control, to the point that a traditional computer just cannot handle that much information, and it takes hours to run an algorithm and to determine the most efficient path. And that's just not something that we can use in the industry, or Amazon could use to operate their vehicles efficiently. So there has to be a better way, is what we're looking at. I mean, how many times have I can tell you for sure, I've seen multiple Amazon drivers come to my house, in the same day. I've seen Amazon drivers in my neighborhood at 8:30, 9 o'clock at night trying to make delivery. So, there's ways that we can improve this. And so I'm going to bring in Alex now to try to talk a little bit about what DWave is doing in the industry, and specifically how some of their demonstration projects and use cases are starting to make a difference. So if you can share your screen now.
Yeah, thanks, Acey. Just bear with me. I don't use Teams very often, so just need to get used to this. Okay. Can you see my screen?
Got it.
Okay. Oops. Just gonna move you over here. There we go. All right. Oops. There we go. Okay. Sorry about the delay. Thanks for the introduction, Dr. Lee and Acey. Yeah, we're excited to be here and talk to you about this. So as Acey mentioned, I'm Alex. I'm from DWave. We consider ourselves the practical quantum computing company. We've been in the business for quite a long time now, so over 20 years. The first 20 years of our kind of existence or foray into quantum computing was really about strengthening our theoretical foundation and making sure that we had a foundation that was set up well to scale and to really deliver value to industry, like the transportation industry. In 2017, we released a more widely available quantum computer called the DWave 2000Q. This had 2,000 qubits, and with this, we were able to demonstrate 100 times speed up on a benchmarking problem. So this was a good early indication that we were on the right track to being able to deliver value to customers and to organizations looking to bring quantum into their business problems. Since 2017, we've made some significant contributions to science. I'm not going to get into that too much because we're here to talk about transportation and applications, but all of that has led us to releasing our current quantum computer called Advantage in 2020. Advantage has 5,000 qubits and 15-way connectivity between those qubits, which in the industry now is a really significant amount and can solve significantly sized problems within the industry. So Advantage has allowed us, or has allowed our customers rather, to start developing early applications. And we even have some applications in a production environment already. So we're starting to see the uptick, and we're really well poised now to continue to expand the application domains that benefit from quantum computing. Our quantum computer is accessible through the cloud. So our quantum computer is shown here on the left. It looks like a big box. This box is about a 12 by 12 footprint, so it's quite large, but the quantum processor inside is very small. This is just a big fridge here that houses the quantum computer. This is accessed, though, through, like I said, the cloud. Leap is our cloud-based platform. So if you were to Google DWave Leap, you could sign up for a free account, get some time, and start exploring our resources, our code examples, and see some examples of what you can do with a quantum computer or with our hybrid solvers, which I'll mention a little bit later. But we've really designed this entire system to be accessible and easy to use for folks who don't necessarily just have a quantum computing background. But that being said, I think quantum computing is kind of fun and quite interesting. So we are going to talk a little bit about what quantum computing is, and specifically what quantum annealing is, because Advantage is a quantum annealer. And so currently, DWave has quantum annealers available online, which is a specific type of quantum computer. So first, I want to introduce a few kind of fundamental concepts in quantum computing. And these three concepts are really foundational to all types of quantum computers, and they're leveraged by all types of quantum computers to provide that kind of added value over classical. Now, the first concept is called tunneling. And so on the left-hand side here, we see what I'm going to call a waveform. So this blue line, we're going to call this a waveform. And in optimization and other types of problems, one way that we can think about solutions to our problem is by modeling it as an energy landscape. So we can think about this blue line here just as a very, very simple energy landscape where the lowest point in that energy landscape represents the optimal solution. So for classical computers to get into this lowest energy landscape or lowest energy point in the landscape, if we had a ball that was located in this higher well, then we would need to thermally excite it until it can jump over this barrier and then settle into that low spot. With quantum, though, if that ball was up in the higher spot, it can actually just tunnel directly through this barrier. So throughout an anneal, for example, it's going to tunnel very, very quickly through this barrier back and forth until the end of the anneal when it settles in the lowest energy landscape. Quantum physics in some ways isn't so different from classical, especially when we're thinking about where systems want to be. So typically systems in classical or quantum, they want to be in the lowest energy configuration. Think about rolling a ball downhill. It wants to roll down to its lowest energy position. And that's kind of similar in the quantum world too. But with tunneling, instead of having like a physical ball, what we end up doing is having this waveform or this probability distribution of the different states that the quantum computer may end up in. So here this is showing that there's a probability or a chance that it could end up in the highest well, but there's also a probability that it'll end up in the lowest well. So now we've introduced this idea of probabilistic computation. The second concept that's really fundamental to quantum computing is one called superposition. So if you think about classical computing, we have bits, right? And bits can be 1 or they can be 0. And we've been able to do a lot of really cool things and complex things with these zeros and ones, but there's also this space in between. Or in quantum computing, there's a state called superposition, which is both states at the same time. So a 0 and a 1 at the same time. And leveraging that can help us find better quality solutions or explore energy landscapes more effectively than classically. And we can visualize this by thinking about an image. So if I have this image here, it's hard to see, but this is actually a dog on a rug. But right now, all of the pixels are either black or white. And so we get this level of detail when we look at this image. If I introduce the grayscale, though, which we can kind of think about as analogous to superposition, suddenly I get all of this additional detail and I can actually see that this is a dog sitting on a rug. And so we can think about the benefits of superposition as being similar to what we see here when we add a grayscale into the image. The third concept is entanglement. And this one is, really, really foundational to all quantum computing as well. Here we're working with 2 quantum states. So on the left-hand side here, I have a blue ball that is a spin-up state. And on the right-hand side, there's a red ball that has spin down. So these are just 2 quantum states. The important part is that there's a relationship between them. So in this case, the relationship might be that when the blue is spin up, the red is always spin down, or it might be that these quantum states are always opposite to each other. But in the presence of this relationship, what I can do is I can have one of those states with me in Burnaby, and then I could send the other quantum state over maybe to Florida, and I can, if I measure one state, I automatically know the value or the state of the other. So we can preserve or know things about one particle despite vast distances between them. Okay, so there are a lot of different ways of building out qubits. Some of these are listed on the right here in this diagram, and there are a lot of different types of quantum computers. When we first started out in this industry, we considered a lot of different factors when deciding what types of qubits to use and what type of quantum computer to start with. The first fabrication and how feasible it is to fabricate and operate the quantum computer. We always knew that we wanted to build a quantum computer that would be useful to industry and to real-world problems. And so with that, we needed to make sure that our quantum computer could scale and was tolerant to noise. We also evaluated the types of kind of industry relevant problems that we thought would benefit most from quantum computing, at least in the near term, and use that information to inform our decision. So where we landed was on superconducting loops and on adiabatic quantum computing. Now, just in the fall, we also released an announcement that we're moving into the gate quantum computing world as well. So we will be pursuing both types of quantum computers, but at the moment we just have our quantum annealers, which are a form of adiabatic quantum computer online. Okay, so I've said this word quantum annealing a number of times, but let's talk about what it actually does or what it means to solve a problem through the process of annealing. And I'm going to introduce this idea by first comparing to classical approaches. And remember how I brought up that idea that we have an energy landscape that can model solutions to a problem or can represent solutions to a problem? I'm going to go back to that idea and I'm demonstrating it here, just a more complex version of that curve that we saw. So on the image on the right here, I have a landscape. Every point on this landscape represents a possible solution to some problem. It could be a transportation problem, it could be another one. The lowest point on this energy landscape represents the optimal solution, and every other point on the landscape represents a higher energy or another potential solution. Whether or not it's feasible, whether or not it's good is another question. But classically, if we wanted to find the optimal solution to this energy landscape, we would have to traverse around it and sequentially evaluate each solution that we encountered. Now, there are heuristic methods that can send us from one place of the landscape to another, but even if we use those, we still have to do this traversal of the landscape. With quantum annealing, though, the process of quantum annealing allows us to essentially evaluate all possible points on this landscape or all possible solutions to our problem at the same time and just arrive at the lowest energy solution, ideally. Sometimes we arrive at a good solution that isn't optimal, but the goal is to end up in this optimal state. So you can imagine that if we're able to evaluate all possible solutions at the same time, we're also able to speed up this computation by a huge factor. I'm going to talk a little bit more in depth about annealing, but this equation at the top here is not important. The main point I'm trying to convey with this equation is that there are two parts to quantum annealing. The first, this initial Hamiltonian, helps us put all of the qubits in superposition and helps us in our starting state. And this final Hamiltonian here is just the problem that we send to the quantum computer. But the math itself, it looks kind of complicated, but it's not important for using the quantum computer. However, what I do want to convey is the process of annealing. And so what happens is we start out in a landscape that looks like this image on the bottom left here, where I have initial Hamiltonian as the label. So you can see that in this landscape, I just have a single well, or it looks like a parabola with a single global optimum or global minima. At this point in time, all of the qubits are in superposition and the processor doesn't know anything about my problem yet. So we're just hanging out in a low energy state. Then as we start to anneal, or we start to solve our problem, we start to actually turn on our problem. And what this does is it morphs the energy landscape around that low energy position that we're hanging out in. So the processor is still at this low energy point, we're just changing the landscape around it. And if we continue to do this over time, what we end up is having an energy landscape that models the solution space to our problem. However, the processor itself is still in the low energy or the optimal position. So that's how we how annealing actually kind of evaluates all possible solutions at the same time. It just builds a landscape that looks like the problem, and it always stays in the ground state. So this is called a ground state computation. Now, we went a little deep there, but I do want to assure you that you don't need to know about the physics to use our system. I just like to introduce it because I think it's really cool, and it highlights how quantum, or one way that quantum is really different from classical. But if you wanted to actually use our system to solve a real-world problem, really all you need to know about is a model that we call the binary quadratic model. And what's important here is that you'll notice there are binary variables, and there are linear and quadratic terms. So this model, or this formalism, can be abstracted and applied to a lot of different applications, or used to model a lot of different problems. So the way that I would start thinking about how to model or solve a real world problem using this formalism is by starting with decision variables. So I know that I have binary variables. At the end of the day, that's how we can think about quantum, or that's how we can think about our qubits, as just binary decision variables. Perhaps in a traffic use case or a transportation use case, my binary variable is, do I want to turn this traffic light on or off? So again, that's binary, and choosing the state of the traffic signal is going to be the decision. I also need to think about the objective, or the problem that I'm trying to solve. What am I trying to maximize or minimize in general? So again, in transportation, that might be minimizing congestion in a city. And then the third thing I think about is, what are the rules that help decide if a solution is feasible or good? So what are my constraints? And that might be that when I'm routing traffic or routing cars, they have to follow predefined roads. I can't drive a car through a city block. It has to go on the roads around the city block. So by using this BQM formalism, we can actually model a lot of objectives and a lot of constraints just with linear and quadratic terms that have binary variables. And that's really all you need to start using our system and modeling these real world problems. Again, the way we would access the quantum computer and submit these problems to it is through LEAP. And we have both Advantage, which is our quantum computer available on LEAP, but we also have hybrid solvers. So we recognize that although 5,000 qubits is a lot right now, it's still not enough to handle real world problems or industry sized problems. So we figured out how to effectively use our quantum computer in tandem with classical resources to create hybrid solvers that can solve much larger problems, but still harness the benefits of quantum. So we have 3 hybrid solvers online that also allow us to explore slightly different problem domains, like discrete variables, or that evaluate constraints more effectively and make it easier for the end user, like the constrained quadratic model solver. And the CQM solver also allows us to work with integer variables in addition to binary variables. So again, it expands the problem domain that we can work with and makes it really easy to get up and running. All right, now that we've talked about quantum computing and quantum annealing, I wanted to connect this back to some use cases that we've seen in the transportation sector. So Denso is a manufacturing company located in Japan. They have been working with our systems for a number of years now. And one of their most recent use cases, it has been around optimizing multimodal transport systems. So similar to what Acey mentioned before, scheduling and routing things like buses is a challenge. And then if you also want to add in other modes of transportation, like rideshare services for perhaps the last mile, that just adds a whole other element of challenge around the scheduling and routing logistics. So they looked at how to schedule both rideshare services as well as public buses using quantum. And then as a second part to that, how to route the rideshare services and the buses in order to like minimize congestion, but also improve or minimize the total time spent in traffic for passengers. And with their formulation, even after they scaled the problem up, which is also a process in itself, they were able to arrive at solutions, feasible solutions that were within a margin of 10%, which is pretty good for this problem area. Now, they've also done some work in their factories with automated guided vehicles. So they use these AGVs to transport material, let's say, from one part of a factory to another. And these AGVs are completely autonomous. So they guide themselves. They have some rules that they follow when they're moving through the factories. But one challenge that they often encounter is that when they come to intersections, well, occasionally there are collisions, but also when they detect each other, they have to stop and negotiate who has right of way, and then they can both resume after they have kind of negotiated that intersection. So Denso was curious about how to reduce that wait time, specifically at intersections, but also how to reduce the collisions. So again, to Acey's point about safety being really important, both in traffic, but also in other autonomous vehicle situations. So Denso looked at this a little while back. And they did find that with their quantum solution, they were able to reduce the wait time for each AGV by an average of 15%. And that included when they were focusing on safety over speed. So this is promising, and I think lends itself well to broader transportation use cases, despite being a demonstration on a factory floor. Volkswagen has also done a lot of work with us over a number of years. They first started their foray into quantum computing, at least with us, by looking at traffic congestion. So they started by looking at historical GPS data of taxis in Beijing, specifically when taxis traveled between the airport and the city center. So they found that taxis tended to take the same route. They would take the main artery between the airport and the city center, and this caused a lot of congestion, as you can imagine. So with that historical data, they were curious about if they could come up with a quantum solution that would reroute the taxi traffic along predefined paths in such a way as to minimize overall traffic congestion. And they found that they were able to successfully do this and do this in a way that outperformed the classical solution that they compared it to. So being encouraged by this, they then decided to try a real-time application in 2019 at the Lisbon Web Summit. And the Web Summit is a conference that brings a lot of tech folks together, like thousands of them. So as you can imagine, that also brings some pretty substantial traffic congestion to the area as well. Attendees stay at hotels spread out throughout the city. There's movement between the hotels, the conference center, the city center, and so it can be a little bit of a nightmare. But Volkswagen developed a real-time system that used demand modeling as well as real-time traffic information to route buses to stops kind of on demand, and then also to route the buses throughout the city from one stop to the next in real time and dynamically to avoid potential traffic jams that could occur. And the feedback they got from bus drivers anyways, was that the bus drivers perceived to have driven along routes that were a lot quicker, and their perception was also that they spent less time in congestion or traffic congestion compared to what they're used to. So that was also promising on the front of traffic flow optimization, as well as real-time applications at scale. And then the last use case that I wanted to mention was one that Toyota and the University of Tokyo partnered to explore, and this was optimizing traffic signals on a square lattice. So they modeled the city as a square lattice that had traffic signals at the intersections, and they were curious to see if they could coordinate the traffic signals in such a way as to minimize the time that traffic is stopped, or to maximize throughput through that square lattice. And they compared their quantum solution to two common classical solutions and found much better results, specifically as they scaled up the size of the square lattice. So yeah, again, that's also indicative of potentially a good fit here in terms of global traffic signal optimization in an area. All right, and with that, I will hand it back to Acey.
All right, thank you very much. I'm glad that you are talking about quantum computing and not me, but it is a little confusing, I understand, but the way I look at it and the way I try to think about it, and this is not even accurate. I think the way I understand it is still elementary, but sort of parallel computing. But it's more, I think probably Alex would say, more exponential computing. So you're talking about looking at multiple patterns, multiple possible solutions that are all being solved simultaneously is kind of the way I look at it. And it's all about how you set up those algorithms and how you frame the project in your code, which is vitally important. But a couple of use cases I wanted to talk about that maybe haven't been approached yet, that I think are prime and ready to see some benefit from this next level. Computing services is really things like large-scale traffic modeling. As digital twin becomes more of a real-life scenario and usable technology, we can build these traffic networks really large in a digital environment, but it takes quite a while to run scenarios from potential development projects or potential road changes or signal timing changes. It just takes a long time to get a result using traditional traffic modeling and computing systems. So, putting a system like this into a quantum computer or connecting it to a quantum computer processor, could see more real time. You could allow you to use this in sort of an operational perspective where you're using a model in a real time traffic operations center and testing potential changes to signal timings hour by hour or during rush hour, and make small changes and see how that affects the model. So there's some real time events here that can benefit from this. Certainly other situations. I use this situation as West Shore Interchange here in Tampa. Everybody's pretty familiar with this area. But if when construction begins here at West Shore, and they have lane changes, or if there's potential accidents that occur that close portions of 275 there, it sort of forces people to take alternate routes, and the traffic starts to back up really quickly because no one really knows where to go or what's the best route, and the obvious alternates start to fill up really quickly. So having faster computing systems that can direct people to take alternate routes, that can see a larger part of the traffic network and a larger part of the city network into sort of an app-based format or some website format, or even if it's some sort of audible 511 system on your phone, could allow people to more quickly react to incidents and accidents on the interstate. Certainly, transit, as we talked about, is an important use case in general for large computer systems and operational systems. But as we're starting to see on-demand transit become a thing, it just creates that opportunity for, well, how are we going to, how do we best approach, that on-demand route, and what's the best route to take to pick up our passenger, or can we combine routes, or, how do I get back after I pick the passenger up? How do I get them to their destination faster and to put that vehicle back into service and pick up the next rider? So there's, that sort of fits into more of a classical, decision-making, traveling salesman problem. But at the same time, as you can see here, 2017, you had digital rideshare passengers were approaching 800 million in 2017. It's estimated by 2025 you might see almost 1.5 or over 1.5 billion riders. So this is an area that is really quickly growing. And certainly automation, AI is the future, I think, of everyone should be thinking about this, and how can we automate systems, all these humans that are making decisions behind the wheel, or at traffic management centers, or with all these different computer systems that are helping us, live our day and be safer on the road. Eventually, these systems can be done faster, quicker, using these it's quantum computing networks and algorithms to make it faster, to start to automate those processes and to make those decisions, in the sub-second level, so that, the people sitting behind those desks or sitting at the car, don't really have to make those decisions anymore, and it can be safer, more pleasant experience for everyone. That's where I want to leave it here and jump over to some questions, if possible. We can talk about some potential scenarios or potential other ideas that are in the industry. Dr. Lee, I'll turn it back over to you.
Thank you. Thank you, Acey and Alex. Very nice presentation, both in-depth methodologies, technologies, and also potential application overview of the use cases. So now I think we can open the floor to the audience, both online and in class. So for online audience, if you want to ask a question, you can just simply unmute yourself and speak out your question, or if you need some time to compose your thoughts, you could just leave a message, and we're gonna check on the message. And for the in-class audience, if you want to ask a question, I need to hand this microphone to you so the online audience would hear you guys. So let's see, do we have any questions from both sets of audiences? Okay, maybe I can start one while you guys are thinking about it, because I think this technology is amazing, and I think if you're I attended the academic conference. 2 out of 4 plenary sessions were talking about quantum computing. So this looks like a very attractive technology, that may be the solution to the next generation problems in various fields. So this question is for Alex. I looked at your methodologies. And so basically, the quantum computing is, in my shallow understanding, is sort of like making computers do parallel computing, just like Acey mentioned. So what is the methods you have were like annealing. We also have like simulated annealing and other heuristics algorithms in operations research, and we can do these, solve them with other techniques like multi-core computers, clusters, and even graphic processing units. So what's the advantages or pros and cons comparing these different computational platforms? Thank you.
Yeah, that's a really good question. And I think maybe the first point I'd like to make is that quantum computing isn't the best option for every problem. So as you've kind of alluded to, there are so many other options. And I think one of the challenges is also finding like what platform is best suited for a particular problem. That being said, quantum annealing tends to be really well suited for problems that aren't super huge. Like Acey did mention that there are terabytes of data that come in, every minute, let's say, in the transportation sector. And that amount of data is still kind of out of reach for our systems. But what we often see is, specifically in operations research and optimization, you'll have problems on a slightly smaller scale that are really, really hard for classical to solve. So for example, with simulated annealing, that approach is really valuable for certain problem domains. However, if you have an energy landscape that's really, really jagged, simulated annealing tends to get stuck in local minima and has a harder time finding those global minima because of the way the energy landscape is characterized. So I don't have a cut and dry answer.
Yeah, well, I think I would offer that that's why it's so important to actually start to run some of these scenarios, to run some of these demonstrations, because that's the only way that the industry will sort of catch up and to find what is appropriate for quantum computers versus other systems.
Yeah.
Thanks. Yeah, it's great to know that there are still problems and issues that we need to investigate and compare. And I would encourage students to check out these different systems and try to, think as the next generation transportation engineers look and try to understand and use these new technologies. Any other questions? From the audience and the classroom? Okay, looks like yeah, this presentation well explains in itself, and yeah, and I think so for I guess that's if you have more questions, and after this presentation we will have Acey and Alex's contact information. And you can send me email or to them, and I can if you send it to me, I'll forward it to Alex and Acey. All right, we see one more question from the chat box. What about the Tesla Dojo computer? Yeah, Dojo computer. That is a question. Do you want to answer, or?
I don't know, Alex, is that a competitor? How does that system rank, or what kind of technology do they have compared to DWave?
I'm not sure. I actually don't know much about that one. So you've left me with some homework.
I think Tesla is trying to create a quantum computer, but there are multiple different types of quantum computers. Like I think it's interesting to talk about how they have, like your system uses a controlled environment, a extremely cold environment to try to block out a lot of the interference. But some other systems use like lasers or other networks. What are those other major types of computers?
Yeah, that's absolutely right. And I would say too, like even different topologies or computation models can kind of mix or match different types of qubits. So I think most other quantum computers that you'll hear about right now are gate model computers or ion trap. And gate model quantum computers, a lot of them that I've seen also use superconducting technology. So they also have to be cooled down to really cold environments. But I think it's worth mentioning that quantum annealers, gate computers, ion trap, quantum computers, all of these models, at least what we're seeing so far, it looks like they will have they'll have their strengths for different types of problems. So I think that in this current quantum landscape, it's not so much like is one winning out over the other. It's kind of like what problems are well suited for different types of quantum computers. And hopefully in the next 5 to 10 years, as gate catches up to where annealing's at, we'll be able to answer that beyond a theoretical level.
Great. Actually, yeah, I can talk a little bit about Dojo because I've been working on like autonomous vehicles. So usually there are kind of like many autonomous vehicles are using more of like uniform or general type of computers that are developed by NVIDIA, like a Pegasus, Orin. And Tesla actually hired an Apple chief engineer or something, actually to redesign their own computational chips to further optimize the computational functions from the general products offered by NVIDIA, because NVIDIA's design is offered to all autonomous vehicle users, but Tesla, they're a company that doesn't like LiDAR and is going all the way to video, right? So they designed computer chips more efficient and optimized towards video analytics. So the computer, this Dojo is mostly based on GPU computational capabilities. And the hardwired neural networks, especially convolutional neural networks, in their chips, so that way they can process the video analytics more efficiently. So that's something that I know about Dojo. But of course, that is it's just like a private technology for Tesla alone. We don't know too much the detail, and I don't think that's quantum computing. It's just like mostly GPU based computing with some specialized hardwires for neural networks. Any other questions? All right, great. Well, we got pretty good discussions, and I just want to thank Acey and Alex again for their great presentation. If you can share your slides with us, we will follow up with you. We can upload it online. And also, yeah, I see some echoes from the audience saying that great talk. Thank you. So that's something I absolutely agree with. And with this, I want to allude to the next week's presenter, Brandon Campbell from City of Tampa, and I believe he's going to talk about some great initiatives within the city, and I hope you can attend. And I want to thank the speakers and the audience again for attending this seminars, and we will see you next week. Thank you.
Thank you.
Thanks, Dr. Lee. Thanks, everyone.